Chapter 20, Coulomb's Law. Coulomb's law covers electric charge, Coulomb's law, the principle of superposition, shear theory, property of charge. You can find them in a timeline. Electric charge. Electric charge. Electromagnetism. The sciences of electricity and magnetism developed separately for centuries until 1820. In fact, when Hans Christian Ørsted found a connection between them. An electric current in a wire can deflect a magnetic compass needle. He is from Denmark. The new science of electromagnetism, the combination of electrical and magnetic phenomena, was developed further by works in many countries. One of the best was Michael Faraday. That talent is attested by the fact that his collected laboratory notebooks do not contain a single equation. He's from the UK. In the mid-19th century, James Clerk Maxwell put Faraday's idea into mathematical form, introduced many new ideas of his own, and put electromagnetism on a sound theoretical basis. He's from UK too. Electric charge. Electric charge is an intrinsic characteristic of the fundamental particles. That is, it is characteristic that automatically accompanies those particles wherever they exist. The positive and the negative labels in science for electric charge was chosen arbitrarily by Benjamin Franklin. He is a great physicist and a politician in USA, the founder of University of Pennsylvania, Philadelphia, in USA. Charges with the same electrical sign repel each other, and charges with opposite electrical signs attract each other. You see, this is a glass hand over, can rotate. If you had positive charge on it, and we take another glass rod with positive charge, close it, and we find they repel with each other, and this rod rotate this way, okay? If we use the opposite charge on the plastic, close it, and we find they will attract with each other, and this rod rotated in this direction.
These pairs of ping pong balls coated with conductive paint will be used to show electrostatic attraction and repulsion. This pair of balls hang on wires from a metal support, so they are electrically connected. If we touch a negatively charged rod to the metal, both balls acquire negative charge and separate because of the repulsive forces between them. This pair of balls is electrically insulated from each other. We'll touch one with a positively charged rod and the other with a negatively charged rod. The balls acquire opposite charges and attract each other until they touch and neutralize their charges.
This Wimshurst machine is used to produce very high voltages. One side of the generator becomes positive, the other negative, until the voltage between the electrodes is great enough to ionize the air between them. We'll use the Wimshurst to put opposite charges on a pair of metal plates. A small pith ball tethered by a thread shows the attractive force between the opposing charges. It picks up a small amount of charge from the bottom plate and is lifted toward the top plate by an electrostatic force. If we drop a conductive ball through this tube and into the space between the plates, the ball bounces energetically between the two plates, transferring charge between them. When the Wimshurst machine stops, the plates are rapidly neutralized by the bouncing ball. When the charge is mostly gone, the ball stops.
Here's a device called an electrophorus, which generates electric charge in an interesting way. It consists of an acrylic sheet and a round metal plate attached to an insulating arm. If we rub the acrylic with a wool cloth, the acrylic acquires a positive charge. The metal plate is then placed on the acrylic. A grounded wire is then touched to the metal plate. If the plate is now lifted off the acrylic and brought up to a second metal plate that is grounded, a spark jumps between the plates. If we repeat the procedure without recharging the acrylic sheet, we can get another spark. And another. How can we continuously generate charge without recharging the acrylic? The electrophorus works by electrostatic induction. When the neutral metal plate is lowered onto the positively charged acrylic, the negative charges in the metal are pulled to the bottom of the plate. That leaves a net positive charge on the top surface of the plate. When the top surface is connected to ground, electrons conducted from the ground neutralize the upper surface. The plate now has a net negative charge. The positive charge is still on the acrylic, so the cycle can be repeated. This device contains a small piezoelectric crystal, which can be squeezed by pressing down on this lever arm. When the arm is pressed, the high voltage generated in the crystal causes a spark to jump between these two electrodes. When the crystal is released, another spark jumps. This animation shows the voltage being generated by the crystal. When the crystal is released, an opposite voltage is produced.
The term electrostatic is used to emphasize that relative to each other, the charges are either stationary or moving only very slowly. The application for electrostatic can be pen spraying, powder coating, flat edge precipitating, non-impact inkjet, printing, photocopy, and decide boy and girl. When woman pregnant, it is boy or girl decided by the charge she carried.
Electrostatic precipitators are often used to remove pollutants from industrial smoke before it reaches the atmosphere. To demonstrate the effect, we'll use this acrylic tube with a metal conductor at each end, connected to an electrostatic generator. Smoke is put into the chamber with each of the conductors hooked up to one end of the generator. The high voltage that is generated sweeps the smoke particles out of the tube.
We'll use this model house and a high voltage electrostatic generator to demonstrate how a lightning rod works. One side of the generator is connected to a metal ball inside the chimney. This sharp rod is also electrically connected to the same side of the generator. The other end of the generator is hooked to this copper sphere, which simulates a charged cloud in the atmosphere. When the generator is cranked with the lightning rod down, large bolts strike the chimney. When the lightning rod is raised, the bolts stop. When the lightning rod is lowered, the large bolts resume.
Conductors and insulators. In some materials, such as metals, tap water, and the human body, some of the negative charge can move rather freely. We call such materials conductors. This is a neutral copper. If we move a charged plastic closer, you see, because the negative charge can move, so it's repaired to the far end, and the positive charge stay there for attracted. In other materials, such as glass, chemical pure water, and plastic, none of the charge can move freely. We call these materials non-conductors or insulators. Semiconductors, such as silicon and germanium, are materials that are intermediate between conductors and insulators. The microelectronics revolution that has transformed our lives in so many ways is due to devices constructed of semiconducting materials. Finally, they are superconductors, so called because they present no resistance to the movement of electric charge. Throw them.
This electroscope can detect the presence of electric charge. When a charged rod touches the top of the electroscope, the pointer deflects. We'll use the electroscope to compare the way charges move in different materials. A rod with two arms is plugged into the top of the electroscope. The right arm is an aluminum rod, while the left arm is acrylic. When we touch a charged rod to the aluminum arm, the electroscope deflects, showing that charge has moved through the aluminum arm. Aluminum is an electrical conductor. If we touch a charged rod to the acrylic arm, there is no deflection. Acrylic is an insulator and does not conduct electric charge. An electroscope and a pair of metal spheres will be used to demonstrate electrostatic induction. If one of the spheres is charged, the sphere can cause the electroscope to deflect. Now we'll start with both spheres neutral. The spheres are placed in contact with one another. The negatively charged rod is brought near, but not touching, one of the spheres. The spheres are separated, and the rod is removed. When one of the spheres is touched to the electroscope, the scope deflects. What will happen if we touch the other sphere to the electroscope as well? The electroscope goes back to zero. The charges induced on the two spheres are equal and opposite. This animation shows how the charges develop on the two spheres as the charged rod is brought near. Electrostatic generators, such as this Wimshurst machine, use electrostatic induction to separate positive and negative charges and can create very high voltages. Here's an animation of a very simple type of electrostatic generator known as a voltage doubler. An acrylic disc with small pieces of metal foil near its outer edge is mounted so that it can rotate when turned by a crank. Two metal shells are wrapped around the edges of the disc. A metal bar with conductive brushes at either end contacts two of the foil pieces at the positions shown. Assume the two metal shells start out with a small imbalance of charge, so that one is more positive than the other. That charge imbalance induces charges on the two foil pieces, which are in contact with the brushes. When the disc rotates, these foil pieces break contact with the brushes. each coming away with a small charge that is opposite that of the metal shell on that side. Each foil piece that follows comes away with the same charge. When these charged foil pieces reach the center of the opposite shell, they contact a conductive brush inside the shell and surrender their charges to that shell. As charge builds up on the shells, the process of induction becomes stronger, leaving more charge on each of the foil pieces and accelerating the charging process. If discharge rods are attached to the shells, a spark will pass between them, reducing their charges and starting the cycle again. Here's an interesting device known as a Kelvin water dropper that generates static electricity from the energy in falling drops of water. Water is allowed to fall from these two droppers through metal rings and into the metal cans below. After a few seconds, enough voltage develops between the cans to flash a small neon bulb. This animation shows how the generator works. Assume a small charge imbalance initially exists between the cans. The can which is more positive is connected to this ring, and the positive charge on the ring attracts negative charges into the droplet at the end of the dropper. The droplet breaks away, carrying the negative charge down into the negatively charged can below and increasing the charge on the can. On the other side, positively charged droplets fall into the positively charged can. The charges on the two cans increase until the voltage is high enough to flash the neon lamp.
Coulomb's law. The electrostatic force of attraction or repulsion between 2 point charges Q1 and Q2 equals to F 1 over 4 pi epsilon 0 Q1 Q2 of R square R hat. The same side repel with each other. Same side repel with each other. Different sides attract with each other. R hat is a unit vector along the line connected 2 point charges and pointing the one in Conserved. If this is the point in Conserved, so this is one towards it along this line. This is R hat. And here, Q1, Q2 both positive. So their product is positive. So that means this is a positive along the R hat. If this is the charge in Conserved, then the same reason, this is a R hat, in this case, is towards it. And in this case, Q1, Q2 is positive. So it is this one. Now look at this. If this is a charge in Conserved, and this would say R hat is along the line and towards it. In this case, Q1, Q2 with different sign. So Q1, Q2 is a negative number. So negative R hat. And this is the direction R hat. So negative is this direction. So in this case, this is direction F. Coulomb is a French scientist. 1 over 4 pi epsilon 0 is a constant, 8.99 times 10 to the 9 unit. And epsilon 0 equal to 8.85 times 10 to the minus 12 unit. Okay. We call it a permittivity constant. The international unit of charge is Coulomb. 1 Coulomb is the amount of charge that is transferred through the cross-section of a wire in 1 second when there is a current of 1 ampere in the wire. The principle of superposition. If we have n charged particles, they interact independently in pairs, and the force on any one of them, let us say particle 1, is given by the vector sum. So F1 means the force acting on charge 1 is equal to sigma F1I equal to F12 is the force acting on 1 by charge 2. the force acting on 1 by charge 3, the force acting on 1 by charge 4, and so on. Okay. Shear theory. Shear theory. A shear of uniform charge attracts or repels a charged particle that is outside the shear, as if all the shear's charge were concentrated at its center. Now, this is a uniform charge shear. Uniform. Attract a charge outside it. It seems that all the charge of the shear concentrated on its center. So this can be simplified like 2 points. This point at the center of the shear. The charge is the shear's charge. The distance is r. If a charged particle is located inside a shear of uniform charge, there's no net electrostatic force on the particle from the shear. This is also a uniform charge shear. The charge Q is inside it, then we say no net electric charge force. We didn't say no electrostatic charge. There is electrostatic forces, but they cancel out with each other. So in this case, the force acting on Q by the uniform charge shear is 0. It's called shear theory. We can prove it later. A point charge Q inside a uniform charged sphere. Now, remember, this is not shear. This is a sphere. Whole body is uniformly charged. Okay. What we do, we can divide this sphere into 2 parts, where the charge Q is on the verge between them. We look at this green one, the shear, the thick shear. The thick shear can be looked at composed of many uniform charge shear, very thin. And the Q is inside this shear. So the electric force acting on this Q by this shear is 0 from the shear theory. Okay? And then look at this one. And this one, Q is on the surface of this ball. And the total charge is Q prime, which is different from Q, smaller than Q, okay? Because outside it takes out. And this sphere can be looked at composed of many thin uniform charge shear. And this Q is outside this shear. For each shear, the reactant, we can think that all the charge of the shear concentrate on the center. So in this way, the total charge force acting on Q by this ball is equal to the total charge of this ball, Q prime, located at the center of the ball, the distance r. This is the way we calculate. Sample. In the figure A, 2 identical electrically isolated conducting sphere A and B are separated by center to center distance A, that is larger compared to the sphere. Sphere A has a positive charge Q, positive, and sphere B is electrically neutral, no charge at all. Initially, there's no electrostatic force between them because one is no charge. Okay. Also, we assume that there's no induced charge because of their large separation. They are far away. Question A. Suppose the spheres are connected for a moment by a conducting wire. The wire is thin enough so that any net charge on it is negligible. What is the electric force between the spheres after the wire is removed? In connectors, the charges are separated in 2. Each one carries half Q. So the charge between these 2 point charges, the force is equal to, according to Coulomb's law, okay, we can put the number. This is half Q. Q2 is half Q. Okay, the R is this distance A, so we get the number is this one. Okay. Question B. Next, suppose sphere A is grounded momentarily, that it becomes zero. And then the grounded connecting is removed. What now is the electric force between the sphere? Now, because this is zero, so there's no electric force between these two. When you ground a negative charge, neutral the charge on it, so it becomes zero. Okay, so there's no electric force between these two because this is zero. Example: nucleus in an iron atom has a radius of about 4.0 times 10 to the minus 15 meter, and it contains 26 protons. Question A. What is the magnitude of the repulsive electrostatic force between two of the protons that's separated by 4.0 times 10 to the minus 15 meter? That's very simple. We put the charge Q1, Q2 proton is equivalent to E, the 1.6 times 10 to the minus 19. Okay, and the distance is 4.0. We put a number inside. Okay, put the number inside. We get a force about 14 Newton. Question B. What is the magnitude of the gravitational force between those same two protons? So we use the Newton's law, Fg equal to G np npr squared. We know the mass of proton. Okay, we know the constant G. Okay, and this R the same. We put them inside. We get this 1.2 times 10 to the minus 35 Newton. Compared to the electronic force, the gravitational force is much smaller. It's much smaller. So we can neglect it when you handle with the electrostatic force. Properties of charge. Charge is quantized. When a physical quantity such as charge can have only discrete values rather than any value, we say that the quantity is quantized. We have already seen that matter, energy, and angular momentum are quantized. Charge added one more important physical quantity to the list. It is possible, for example, to find a particle that has no charge at all, or a charge of 10 electric charge or minus 6e, but not a particle with a charge of, say, 3.57 e. The minimum charge quantum is e. Okay, any charge should be multiple integral number of e, where n can be plus minus 1, plus minus 2, and so on. And the quantum of the charge is small. We call it E is 1.60 times 10 to the minus 19 Coulomb, which is the electric charge or the proton charge. The elementary charge E is one of the important constants of nature. The electron and the proton both have a charge of magnitude E. Quarks, the constituent particles of protons and the neutrons, has charge of E over 3 or 2E over 3, but these apparently cannot be detected individually. Hence, we do not take these charges to be the elementary charge. You should keep in mind, particles are the substance and charge happens to be one of their properties, just as mass is. Charge is conserved. This hypothesis, or conservation of charge, first put forward by Benjamin Franklin, has stood up under close examination, both for large-scale charged bodies and for atoms, nuclei, and elementary particles. No exceptions has ever been found. Thus, we add electric charge to our list of quantities including energy and both linear and angular momentum that obey a conservative form. Radioactive decay. U-238 decay to thorium-234 plus helium-4. You see the charge, this is a 238 proton, 238E. This is a 234 proton. 4 protons put together, the charge conserved. Annihilation. The electron plus positive electron, negative plus become 2 gamma rays, then neutral. Next chapter, chapter 31, electric field. Welcome you make a comment and give suggestions so that this program can be more helpful. Acknowledgement. This video clip is a part of my lectures on college physics during 1990 to 2021, based on the adapted textbook, Principles of Physics by Holliday, Resnick, and Walker, published by Wiley. The demo videos were bought from a company in USA by my university for teaching. They helped a lot. I'm sorry for not remembering its name to show my appreciation. It seems that they came from the University of California, Santa Barbara, where I got my PhD in physics. Thanks God.